If you were given a circuit like this one shown, and you were asked to find the total voltage supplied by the circuit to the load resistor notated here as RL, what would you do? We can see here that we have several resistors here in series and in parallel, as well as a few voltage sources, so we would need a method in which we can simplify this circuit to find these overall equivalent values. Today's video will be diving into two similar methods in which this can be accomplished, known as Thevenin and Norton circuit equivalents. Thevenin and Norton equivalent circuits are used to simplify complex circuits into either a single current or voltage source and a single resistor, allowing for the evaluation of a load.
Thevenin equivalent circuits are a linear circuit which can be simplified to only a single voltage source and a single resistor in series, as shown on the left.
A Norton circuit is a linear circuit that can be simplified to only a single current source and a single resistor in parallel, as shown on the right of the screen.
The steps to solve the Thevenin circuit are shown below. The first is to make sure your circuit is linear. Then choose network A and B. You will be simplifying A and leaving B alone, as it will contain the load. Next, separate network A from B. Solve for VOC.
The most typical method to do so would be using a voltage divider, which is what we will show you today.
Then make all circuit elements inactive by shorting voltage sources and opening current sources. Then calculate REQ.
REQ, otherwise known as the equivalent resistance, is calculated using series and parallel resistor rules to find one singular value for the entire resistance of the circuit.
Finally, draw VOC in series with REQ and connect it back to the load B.
Solving a Norton circuit equivalent is very similar to solving a Thevenin equivalent. So the first step is to make sure that your circuit is linear, and then you will divide the circuit into networks A and networks B. Network A is what you're going to be simplifying using the Norton method, and B is going to be your load. So once you have these networks separated, you're going to short circuit network A and solve for the current through that short circuit, otherwise known as the Norton current. It's going to be the value of your current source that's going to be in parallel with REQ. So we've solved for REQ previously using methods that we've previously discussed. And then lastly, the final step would be to draw your current source with the value of the short circuit current in parallel with REQ and connect it back to the load in network B.
This circuit will be serving as our example problem for both the Thevenin and Norton equivalent circuit. The first step is to separate networks A and B.
For this example problem, we will be using the same networks A and B for both the Thevenin and Norton equivalents.
First, we're going to begin by simplifying the circuit. Because we're using the same network A and B, the same circuit simplification will be used throughout the problems. First, we will combine the resistors in series on branches 2 and 3. Next, we combined all parallel resistors to create one common resistor. When looking at the circuit on the right, the 5 ohm resistor is 0 because it is not a participant in the closed circuit. Next, we will be solving for the open circuit voltage. Using the simplified circuit on the right, it can be seen that the open circuit voltage is equal to the voltage across the 1.53 ohm resistor because the 5 ohm resistor is not relevant. Next, we calculated the open circuit voltage by taking a voltage division of the simplified circuit in the previous slide. The open circuit voltage was calculated to be 4.06 volts. Next, to calculate REQ, we will have to short the voltage source and combine all the resistors. It can be seen that the 6 ohm and 1.53 ohm resistors are in parallel, and when combined, they become in series with the 5 ohm resistor. The final REQ value will be 5.82 ohms, and it will be the same REQ value used in the Norton equivalent circuit calculation. Finally, you combine the VOC in series with the REQ and connect it back to the load. Congratulations! You've found the final Thevenin circuit.
Using the same method of circuit simplification as shown previously, we are able to derive this simplified circuit, except in this case, we will write the final circuit in terms of a current source, so we will want to short this circuit and work it in a way to find the current through this short circuit. The first step in doing this is finding the voltage at the point in this circuit, which is calculated here as shown to be 2.48 volts. This value is then used to calculate the current of the short circuit, which is equal to the current source of the Norton equivalent, using Ohm's law. This results in a current of 0.496 amps. The last unknown that we have to solve for is Req, which as previously stated is the same as the Thevenin Req value of 5.82 ohms. By combining the 0.496 amp current source in series with Req and connecting back to network B, or the load, we arrive at the final Norton circuit equivalent as shown.